Hey, I wrote this code. What do you think?
It's fetching to check and fetching to use.
Okay, so?
What if in between that time, your variable buffer size changed?
You can't do that.
Ah, but you can. When a program runs, a system doesn't only dedicate all of its resources to that simple program, other things run concurrently.
What? I thought I was at the center of the universe.
Sadly, that is not the case. The system still needs to run other programs to make computing a seamless and wonderful experience.
Timing-bound kernel vulnerability in the Microsoft Windows anti-kernel can be caused by race conditions via memory access patterns. Let me explain why this subject is so interesting. Up until 2013, there's only been one double fetch vulnerability publicly discussed. This was exposed by Thomas Garnier back in 2008. However, no further research was done until the Bashman project. This was a very real threat affecting all previous Windows versions, so why wasn't it explored until 2013? According to Jonathan Morrison, Microsoft was in fact well aware of this problem, but didn't want to deal with it. Bryan was originally researching a different topic when he noticed that his code was acting glitchy, so he investigated more and found that the issue was shared across 26 other internal syscalls.
Well, at least they started caring about it and tried to fix it with Windows 10.
Wrong. The vulnerability was actually accidentally eliminated. If we investigate carefully, the code still has the double fetch vulnerabilities and still uses a user mode region to fetch a pointer for further use, but only does this once. However, the reason the vulnerability is no longer an issue is because the Windows 8 compiler has been optimized.
So, what is the basic idea behind race conditions, memory access patterns, and the kernel?
The Windows kernel provides support for multi-threading and separated user system address space on separation of privileges. The user portion of the memory can be accessed by both ring 0 and ring 3. The kernel address space, however, can only be accessed by ring 0. To securely implement the system, ring 3 can only access space in ring 0 by calling predefined system calls with the correct permission. The system call handler is solely responsible for the fetches of memory pointers. Thus, the lack of proper transferring of input from ring 3 memory region gives us a window to exploit that can range from leaking of private information to escalation of privileges.
A race condition is the behavior of electronic systems where the output is dependent on uncontrolled sequences or timing. For example, say a chicken farmer counts up the eggs in a coop to know how many buckets to bring for collection. In this example, let's say the farmer can fit 4 eggs per basket. First, the farmer counts up how many eggs are in the coop. This is known as time of check. Then, they go to get the appropriate amount of baskets so they can pick up all the eggs. The time of pickup would be the time of use. What if a chicken laid an egg in between the time of check and the time of use? The farmer might not be prepared to take all the chicken eggs back home. In these cases, a race condition is defined as an unexpected change of a variable between the time of checking that variable and the time of using that variable.
How does double fetch vulnerability affect me?
In general, there are 4 exploits associated with this vulnerability: buffer overflow, write what where, read where, and read garbage conditions. Consider this simple code. This shows how a typical buffer overflow can occur. Notice how the Windows device driver tying the size of buffer from the user mode was reused as a parameter in the RTL copy memory call. This is effectively introducing a potential pool-based buffer overflow vulnerability. Now, let's take another example. The example shows write what where vulnerability. Write what where is the result of inconsistency between a user-controlled pointer during sanity checking and the one used for actual memory location. Here we can see that the LP input pointer is fetched once to check and fetched again to use in the function RTL copy memory. This is subject to time of check to time of use issues. In simple terms, the values could have changed in between the check and the use because of the concurrency of programs.
Read where is a result of inconsistency between validated and used input pointers, thus causing a memory leak into user mode. Read garbage is the opposite of buffer overflow. This happens when the buffer is filled less than its size, thus passing the contents of uninitialized kernel buffers. To show you what a buffer underflow attack looks like, we have constructed the code on the right. As you can see, there is a very large buffer. In this buffer, we are storing too small of data to actually completely use up the buffer. So, when we print out the contents of the buffer, we have the first few bytes that we have filled up, and then we have garbage. In some cases, this garbage can contain secret information like passwords and other very private things.
So what's new? How can we detect this user fetch and user use problem?
For this, we need to talk about how Bashwin first found this bug. A double fetch vulnerability manifests when, first, two distinct same-size memory chunks are read from the same user mode memory location, with both reads taking place. Second, the reads are within a short time frame. Thus, memory access pattern analysis, or the ability to log and monitor memory reads performed by an OS, gives us an opportunity to find such vulnerabilities. In the case of Bashwin, a virtual machine was run with different versions of Windows. It logged all the accesses to memory that occurred during runtime, flagging any instances that resembled a double fetch.
How do people generally exploit this?
There are a few main techniques used to exploit double fetch vulnerabilities, which include memory caching and write combination, page boundaries, TLB flushing, flipping operation, thread management, and priority classes.
Let's look at a simple case below to see why we use these techniques. In the example below, we can see that the number of instructions between check and use of a variable is quite small. So how can we exploit this?
A simple way to increase the time of execution is to manipulate memory caching and fill up the cache with junk so that the runtime of the program would be longer. Alternatively, we can also turn off cache for a system. Write combine is not subject to caching, thus is a great alternative to manipulate the program with.
Page boundaries are used when the attacker uses little endian ordering in the x86 architecture to make the more significant bits of a number be stored at higher addresses, allowing more time for the exploit to occur.
The third technique is flushing the translational look-aside buffer, or TLB. TLB is responsible for caching pages referenced in a thread. It can provide us with two main advantages. First, the process of fetching data from virtual memory doubles the work done by CPU as it requires it to read across two memory pages. Second, by using APIs such as the empty working set function, the TLB cache gets flushed, thus significantly increasing our window of attack.
Flip operations are used to change small values such as pointers or data up to 4 to 8 bytes. One method is to XOR with OX 8 followed by zeros. This flips the pointers from user to kernel mode between check and use very quickly. This is a very fast way of beating a race, but it comes with the cost of doing nothing exploitable half the time since we would just be looping through bit flips. Another method is to use an increment command for the data we are changing. This guarantees a change in the value between check and use, but this makes it difficult to control or know what specific value was used in the end.
Thread management is another vector by which the window of attack can be increased. This depends on whether the exploiting function and the function to be exploited are running on the same chip, known as hyperthreading, or if they are running on separate chips. In the case of hyperthreading, the attack is best done with cache pages where there are multiple threads trying to exploit the double fetch vulnerability. If there is no hyperthreading, the most efficient exploit would be to disable caching and use a combination of techniques that focuses on making the fetch operation as slow as possible while not affecting the flip increase operation.
Priority classes, as they sound, make sure your exploit has the highest priority possible. This can be done with APIs that manage thread priority such as setPriorityClass and setThreadPriority. The main goal of using this technique is to make sure the system spends more time running your exploit than the thread to be exploited.
There are so many attacks. How can we defend against this?
There are a few ways to mitigate the attack. One idea would be to use ASLR. This would make it difficult for the hacker to guess the address within the program and certain access files. However, it is easy to find the space layout of the exploitation using race conditions. Another idea would be to try and use stack canaries since it would be helpful against buffer overflow attack. However, the value of these canaries is easily found with race conditions as well. Thus, these mitigations are simply obstacles, simple ones.
How then does someone effectively prevent this attack?
This obviously will depend on what exactly is happening in each case, but the solution that tends to most easily cover all bases is to store a local copy of the variable in question. Take a look at the following code. The issue again lies in the double fetch of the LP input pointer. To eliminate the chance of a race condition exploit, we can do the following. 1. Copy the contents of what is at the pointer into the local buffer while making sure to limit the number of bytes to be copied. 2. Check if the local copy ends in a null byte to know if the contents fit the 256 byte limit set by the code. 3. Save the size of the contents located at the pointer locally and use that to limit how much is copied to the buffer. In the end, Each case will have its own elegant solution.
This is a lot to take in. Can you summarize it for me?
The takeaway would be to understand that there are potential vulnerability in the Windows NT kernel due to race condition in between fetching and using a variable.
Also, that we as coders have to be careful to minimize double fetches.
Awesome!